Welcome. In this video, you'll learn what is convolution and how it works with clear visual examples. Then we'll dive into MATLAB to see how convolution is implemented, manually with built-in functions and using FFT. You'll also see how it compares to cross-correlation and how it's used for edge detection in image processing. Let's get started. Convolution is a mathematical operation that combines two functions or vectors to produce a third that shows how the shape of one is influenced by the other. Here's how it works. We take the second vector, flip it, and then slide it across the first one. At each step, we multiply the overlapping values, sum them up, and record the result. As we shift flipped vector across different positions, we repeat the same process, and the collection of all these sums forms the output. And here's something interesting. If you're familiar with the correlation function, this might look very familiar. That's because convolution is almost the same as cross-correlation for real valued signals. The key difference is that in convolution, the second signal is flipped before sliding. If you're unsure how correlation works, check out our other video where we explain it in detail. Let's now take a look at 2D convolution. Imagine we have an image represented as a two-dimensional matrix. To process it, we apply a 2D kernel, a small matrix that detects specific patterns, like edges or textures. The output is often called a feature map. We start by placing the kernel over the top left corner of the image. Just like in the 1D case, the kernel must be flipped before we apply it. We then multiply overlapping elements and sum them to get the first value in the feature map. The kernel slides across the image one step at a time, repeating the same operation to compute each output value. At the image edges, we can't fully overlap the kernel, so we apply padding. This can be zero padding, where we assume values outside the image are zero, or circular padding, where values wrap around from the opposite edge. After processing the entire image, we're left with a new matrix, where features like edges stand out clearly. Stick around. Later in the video, we'll show this process in action on a real image. Now, let's switch over to MATLAB to see convolution in action. We'll look at how to calculate it in 3 different ways, compare it with cross-correlation, and finally, use it for edge detection in an image. You can find the full code linked in the video description. First, we clear the workspace and close any open figures. Then, we define the sampling frequency, 500 Hz in this case, and create a time vector that we'll use to generate our signals. We also set the length of the convolution result and define a time lag vector for plotting. Next, we generate 2 signals, a rectangular pulse and a sinusoid. To compute their convolution, we start with the simplest method, MATLAB's built-in function. It takes the 2 signals as inputs and returns the convolved output. But to really understand how convolution works, let's also compute it manually and compare the results. We first flip the second signal, just like we explained earlier. Then, we pad both signals with zeros, placing the rectangular pulse in the center and the sinusoid at the start. You could also use circular padding, which wraps the signal around, but we'll stick with zero padding here. Now we use a for loop to slide the sinusoid across the rectangle, shifting one sample at a time. At each step, we multiply the overlapping values and sum them to get the output. Finally, we compare the result with MATLAB's function and compute the error. As expected, it's nearly zero, confirming that our manual method works. Now let's look at a third method, convolution via the frequency domain. Convolution has a powerful property. In the frequency domain, it becomes simple multiplication. To demonstrate this, we'll calculate the spectra of our two signals using the fast Fourier transform. Then, we multiply the two spectra point by point and use the inverse FFT to transform the result back to the time domain. Let's plot the output. As you can see, all three methods, built-in function, manual, and FFT-based, produce the same result. Now let's compare convolution and cross-correlation. First, we calculate the convolution of our two signals using the MATLAB's function. Then, we use MATLAB's xcor to compute the cross-correlation. Finally, we flip the second signal and run xcor again. This simulates the flipping step in convolution. Let's plot the results. As you can see, the standard xcor output differs from convolution. But once we flip the second signal, the results match perfectly. This confirms that convolution is essentially cross-correlation with one vector flipped for real-valued signals. In the final part of this video, let's see how 2D convolution is used for edge detection in images. First, we load an image. It's stored as a 3D matrix with RGB color channels. But for edge detection, we don't need color, so we convert it to grayscale using the RGB to gray function. Next, we define a 2D kernel. Different kernels serve different purposes: edge detection, sharpening, blurring, and more. Then, we apply the convolution using MATLAB's conv 2D function with the same option to keep the output image the same size as the input. Finally, we save the result to disk. As you can see, the edges in the image are now clearly highlighted, all thanks to convolution. And that wraps up this video. If you'd like to keep learning, be sure to check out the next episode in the DSP Fundamentals series. Thanks for watching.